Hello everyone, my name is Amir Sohail Khan and today I'm going to present our paper that we sent to the Conference of Artificial Intelligence in Energy and Infrastructure. Our topic name is MobileNetV3 for Pipeline Welding Defect Detection, a computer vision approach on noisy RGB images. So first of all, I will discuss the model abstract, that what we have in our model. The aim of the project is that we have to design a computer vision approach for detecting the defects of our welding pipelines on noisy RGB images using a very lightweight approach known as MobileNetV3. The main target of our research is to design based on the premise of a pipeline industry to avoid the different welding defects occurring in a pipeline. The programming language that we used for our model was Python coding, and we used two types of dataset for our research. The first one was publicly available dataset that is known as AI 5083, and the second dataset was our self dataset PWDID. The images that we used for the AI 5083 was 4927, while for the PWDID it was 78 images. And the accuracy that we got for the publicly available dataset was very nearly to 100%, means 0.99%, while for the pipeline weld defect inspection and accuracy that we got for the PWDID was 97.44% for pipeline weld defect inspection. The reason that we got a little bit less accuracy for PWDID was because the number of images in the PWDID dataset was a bit less in comparison to the publicly available dataset AI 5083. Our presentation have four main contents. The first section will be introduction, second one methodology and datasets, third we will discuss the results, and in four we will conclude our presentation. So the first part we will discuss the introduction. In the introduction we will say the problem and purpose. What was the problem and what was the purpose of designing this model? Because pipelines have a good safety record, this is due to a combination of good design, materials, and operating practices. But there is a time when, like any engineering structure, pipeline also fail occasionally. Some of the main causes for their failure are welding failures, which leads to various pipeline cracks, corrosion, and environmental changes, which also affects the pipeline. So currently various methods are used for these kind of defects, but the computer vision based systems, due to huge amount of data, can capture machine learning development algorithms. This kind of method have a very huge demand in the present and also in the future. So therefore the main objective of our work is also to propose a lightweight CNN that can work on both small and large data sets. And such kind of CNN framework is designed to address the available best method that can help to detect the defect of pipeline and prevent them from further damage. Then we have to why we needed this design. The main reason was because of the inspection of pipelines is very necessary, as it can prevent pipeline bursts, cracks, fractures, and many other failures. The defects can affect pipeline life and installation and increase probability of disasters. So in order to prevent such kind of disasters, therefore we propose this design, and the usage of this design was to reduce disasters, extend the life of the pipelines, prevent emergencies, monitor and keep track of the different weld defects. The advantage was to a professional weld pipe inspection will detect small issues within the system before they turn into costly emergencies, and by making preventative moves we can extend the expected lifespan of entire pipeline system. The second part is the methodology and dataset. For the data set, we already discussed in the abstract as well that we have two kinds of data sets. The first one is AI5083. As we can see that this data set is consists of the RGB images, and the second one is our publicly our self dataset PWDID dataset. This dataset we captured the images of the real pipeline from the camera in pipeline industry. Now coming to the main method that we used for our model, and that is MobileNetV3. MobileNetV3 is a lightweight and efficient convolutional neural network designed for high performance with low computational cost. It combines depth-wise separable convolutions with advanced techniques like squeeze and excitation and neural architecture search to improve accuracy. V3 achieves a strong balance between speed and accuracy, making it suitable for real-time and resource-constrained applications. We use two types of version for the MobileNetV3 in our design model. The first one is MobileNetV3 large and the second one is MobileNetV3 small. The large we use for the dataset AI5083 because the number of images in their dataset was over 4,000. It was 4,927 to be exact, and for that we needed a large version of MobileNetV3. The second one was MobileNetV3 small because that we used on the PWDID dataset because the images were very less, only 78 images, and for that we didn't need a large version, as we used a very lightweight version MobileNetV3 small on that one. And as you can see in the figure, MobileNetV3 is the feature-based extractor in the computer vision structure proposed in both scenarios, and the output feature vectors of the feature extractor are subjected to fully connected layers to classify the defects in weld in multiple categories. These are the different parameters that we have used for our Python coding that we design and train the model, both the MobileNetV3 small and large, for using the PWDID dataset and AI5083 dataset. Now coming to the third part for our results. For the results, before we go to the results, this is the overall workflow of our method that we used for our design. You can see automated MobileNetV3 for pipeline welding defect detection. This is the overall flow, starting from the load 5 images to the pre-processing images and the image pre-processing, including the augmentation, image execution, and the performance. The last one is performance evaluation and output. The results of by using the AI5083 dataset, you can see in the table that we got the per class matrix for each defect, each weld defect. You can see the overall accuracy we got was 99, and it was almost 100% that we got the accurate results for using this dataset. The second was using the PWDID dataset. You can see the confusion matrix and training versus loss epochs are also there, and the per class matrix, you can see the per class matrix accuracies we also have there, and the overall accuracy, the final one, was 97.44%. The evaluation metrics that we used for our method was accuracy, precision, recall, and F1 score that we used for our model. Now coming to our final part, conclusion. A lightweight deep learning framework based on MobileNetV3 was proposed in this presentation. The model integrates image preprocessing, data augmentation, and CNN-based feature extraction for multi-class classification. The framework was evaluated on two datasets, AI5083 and PWDID dataset that we already show. And we can, from this whole scenario, we can say that the strong performance was achieved without applying denoising even under uncontrolled environmental conditions. The model demonstrated robustness, scalability and suitability for real-time resource constrained industrial applications, and the future work of our design will focus on expanding the dataset and integrating denoising techniques to further improve the real-time industrial deployment. So that's all from our presentation, and in the end we extend our thanks to the SSHMC lab for supporting this project. That's all. Thank you.